Okay, we retain another integral. This one's from nowhere. Okay, we retain another integral. We've got the integral from 0 to 1 of x squared times square root 1 minus x squared dx. Okay, I got the idea for this recently doing another video, and I came across a problem very similar to this, and what I did is I solved this using the beta function. And that works really well doing it that way, but I also know that a lot of people aren't familiar with the beta function, so I wanted to do this one today using straightforward methods. And you just notice here that we could do this using trig substitution. And something in this form for the trig substitution, what I want to do is substitute x for just sine of t. Take a derivative, let's get our dx value. So dx is just going to be cosine of t dt. And the reason this is going to work nicely is because for this 1 minus x squared value, that's going to be the same thing as 1 minus sine squared of t, but we have the identity that we can write this as cosine squared of t. So let's just go ahead and let's substitute this. So first plug in 1. You know what, let's get a value. Let's isolate t. So taking arcsine on both sides here, we can just say t is going to be equal to arcsine of x. So first take 1, plug it in here. So arcsine of 1, that's just going to happen at pi over 2. And then 0, arcsine of 0, that's just 0. X squared, this is going to become sine squared t. Then inside the square root, we've got this. We're going to have cosine squared t, and our dx value is going to be cosine t dt. But then we can simplify a little bit because we've got cosine squared inside the square root here. So what's going to happen when you simplify this is going to be the same thing as absolute value cosine of t. But you'll notice our bounds are in the first quadrant, 0 to pi over 2. Cosine's always positive, so we get to drop the absolute value here. So then let's take this cosine, multiply it here, and we're going to end up with a cosine squared. So rewriting it, this is going to reduce down to sine squared t times cosine squared t dt. And I think the way I want to do it in this case is if we have 2 sine t cosine t, that's going to be sine of 2t, that's going to be our double angle formula, but we've got this whole thing squared. So if I square this 2 squared or 4, then this whole thing here, this is all going to be sine 2t squared. But of course I don't want to change it, we just multiply by 4, so I'll multiply by 1/4 in front. So then let's rewrite this again. But now what I'm going to do is, now rewriting it, I'm still going to want to reduce the power on this sine squared 2t, so we integrate it. So let's do that kind of all in one step. So we've got our bounds the same. For this, I'll use the formula and write this as 1 times, no, sorry. So using the formula on this, we'll write it as 1/2 in front, 1 minus cosine double angle that's already doubled. So double that and we get 4t, and then this is just going to be dt. So then before we integrate, let's just take this 1/2 out front, multiplying it by this 1/4, and this is going to become 1/8 here. Go ahead and integrate. We'll have our 1/8 out front. Integral of 1, that's just going to be a t. Integral here of cosine 4t, let's do that as sine 4t. We bring the 4 out in the denominator. We've got a 1/4, and we just need to evaluate from 0 to pi over 2. But just notice when you plug 0 in, sine at 0, 0, t at 0, 0, the whole thing, we can ignore the 0 part. Plug in pi over 2 here. We're going to have 1/8 times pi over 2. Now when you plug pi over 2 in here, 4 times pi over 2 is 2 pi. Sine at 2 pi is just going to be a 0. So we can ignore this, distribute in the 1/8. For my final solution to this, we just get pi over 16. Okay, there you have it. Skipping the beta function, doing the trig substitution. Thanks everyone for watching. Have a good day.